So the radio waves, if you had enough power in radio waves to generate a light bulb, to power a light bulb,
since 1988, Earth has been receiving a signal from space every 22 minutes. This burst of radio energy arrives with a delay ranging from 30 to 300 seconds, and its strength varies, sometimes being barely detectable and other times blinding. It can take the form of a single flash or a series of minor flashes before and after the main signal. However, every 1,320 seconds, a signal reliably appears, although occasionally it doesn't. This raises the question of whether this represents an undiscovered type of phenomenon, or if there might be an intentional message from an external source. In this episode, we'll discuss where was these signals coming from. This is Reveal the Mystery. If you are curious to learn mysteries of the world, space, and beyond, consider subscribing. The source, designated as GPMJ 183910, is situated approximately 18,000 light-years away. It emits pulses that can endure for varying durations ranging from 30 seconds to 5 minutes. These pulses can occur at any moment within a time window slightly exceeding 6.5 minutes, centered around 22 minutes after the preceding pulse. This might appear as considerable variability to us, given the substantial contrast between 30 seconds and 5 minutes, along with the pulse arrival fluctuating by more than 6 minutes, indicating an unstable source. However, the dynamics of neutron stars can be exceptionally intricate, and if GPMJ 183910 is indeed a neutron star, numerous factors can influence the duration and timing of the received pulses. Astronomers found a signal in 35 years of data, revealing a celestial object that rotates every 21 minutes and 58 seconds. Surprisingly, it has maintained this speed, defying expectations that it should slow down over time. The rotation might have only changed by 0.28 milliseconds, showcasing its extraordinary stability, usually seen in faster pulses that act as cosmic timekeepers. This challenges our understanding of how pulsars typically slow down as they emit energy. Pulsars are a special kind of space thing called neutron stars. These neutron stars are what's left when really big stars die. They're very dense, even more than black holes. Atoms are mostly empty because the electrons whiz around the central part called the nucleus, which is tiny. Now picture a star made entirely of the particles from the nucleus with no electrons, no protons, and no empty spaces. Even a little bit of this stuff, like a tiny spoonful, would weigh as much as 11 times all the people on Earth combined. A typical neutron star is about 35% heavier than our Sun, but it's packed into a sphere that's as small as the island of Manhattan. That's how incredibly crowded they are. What's really interesting is that in this extreme environment, neutron stars make super strong magnetic fields. These magnetic fields are vital in producing the signals we detect from pulsars. To understand where the light waves from pulsars come from, we have to explore a complex process where light and stuff multiply really fast, all starting from just one tiny particle called an electron. Close to the magnetic poles of a neutron star, something interesting happens. A tiny particle, electron, and the strong magnetic field around the star speeds it up. This electron then releases a special kind of light called a curvature photon, which moves along the magnetic field line and starts what we call a pulse. This curvature photon keeps moving straight until it reaches a certain angle compared to the magnetic field. At that point, the light disappears and gives its energy to a bunch of other particles called electrons. Plus, it creates an electron's partner, which is called a positron. This electron-positron pair has some energy that's not in the same direction as the magnetic field lines. They use this extra energy to make more light, known as synchrotron photons. These photons can also create more electron-positron pairs when they reach that special angle compared to the magnetic field lines. This process repeats over and over, making more and more photons and electron-positron pairs until there's not enough energy left to make more pairs. Then, these photons shoot out into space, while the original electron keeps doing its thing as it goes along the magnetic field lines. All of this is why the light from a pulsar is so bright that we can see it even when it's really far away, thousands of light years. But why does it look like it's blinking on and off instead of shining continuously? Well, that's because the magnetic poles of a neutron star are not in the same direction as it's spinning. So these pulsars are like big lighthouses, and their beams of light sweep across space as they spin. For us here on Earth, we see these beams passing by again and again as the pulsar rotates. These are the light pulses that telescopes can pick up. But the light has a very long wavelength, like radio waves, so you need a special kind of telescope called a radio telescope to detect it. The light generated by this cascading process exhibits the same wave characteristics, with these waves neatly aligned, resembling soldiers in formation. This alignment strongly suggests that the source is a neutron star, supporting our hypothesis concerning the 22-minute signal. Additionally, within our signal, there are instances where the light's alignment undergoes abrupt changes, akin to making a 90-degree turn in a car and then returning to its original orientation. This phenomenon further indicates that the signal originates from the poles of a pulsar where these cascading events occur. The signal, although pointing to a pulsar as the source, presents a major puzzle due to its slow rotation and remarkable stability. Pulsars should slow down and eventually stop emitting light, but this signal shines brighter than it should for its slow rotation. Unlike typical rapidly spinning pulsars, it rotates very slowly, yet it remains surprisingly stable, defying expectations of significant deceleration for a neutron star. This anomaly challenges our understanding of how pulsars typically evolve. Researchers are considering an alternative explanation. The source may not be a conventional pulsar, but rather a magnetar. A magnetar stands as a distinct class of neutron star with an immensely potent magnetic field, surpassing that of ordinary neutron stars. Magnetars are renowned for undergoing star quakes, intense events that relieve stress in a neutron star's outer shell. When a rapidly spinning magnetar decelerates, it can momentarily deform, forming a bulge due to centrifugal forces. During the adjustment towards a new equilibrium, the outer layers shift, temporarily realigning magnetic fields and emitting detectable light on Earth. The most powerful starquake on record, originating from the magnetar SGR 1806-20 in 2004, released an astonishing amount of energy. Had it occurred within 10 light-years of Earth, it could have resulted in a mass extinction event. The occurrence of starquakes offers a compelling hypothesis for elucidating the 22-minute signal's origin. Despite its close proximity of approximately 18,000 light-years, we've not detected X-ray emissions from the anticipated starquakes. Additionally, it's atypical for a magnetar's outburst to persist for over 3 decades. Usually, starquakes are brief events with energy dissipating within a few years. The prolonged duration of this signal, if indeed from a magnetar, remains puzzling. This prompts speculation about alternative sources. The astronomers suggest a magnetic white dwarf, a star remnant too light to become a neutron star. If this white dwarf boasts an exceptionally strong magnetic field, it could emit similar radio signals. Unlike neutron stars, white dwarfs exhibit slow, steady rotations, aligning with GPMJ 183910's behavior.